we introduce the ManiFeel, benchmarking and understanding Visuotactile manipulation policy learning. ManiFeel provides a scalable and reproducible benchmark for studying and evaluating Visuotactile policy learning, offering new insights into contact-rich robotic manipulation across diverse tasks and scenarios. Below is a summary of our contributions. We begin by showcasing the simulation rollouts of insertion tasks. ManiFeel includes 4 contact-rich insertion tasks: plug insertion, USB insertion, power plug insertion, and gear assembly. Next, we present the simulation rollouts for the screwing tasks. In both the nut and bolt and bulb screwing tasks, tactile force field feedback provides more stable and consistent control during the tightening process. We now present the simulation rollouts for the exploration tasks, which include 3 representative scenarios. First, in the peg reorientation task, where the external camera view is completely blocked, the robot must blindly reorient the peg, align it, and insert it into the internal socket. The vision-only policy fails to perform fingertip reorientation for alignment, while the Visuotactile policy successfully reorients and inserts the peg. Second, in the object search task, an object is placed inside a container, where the external camera view is completely blocked. The robot must explore, locate, and retrieve it. The vision-only policy often explores randomly and lifts the gripper without finding the target, whereas the Visuotactile policy detects contact cues through tactile feedback and successfully retrieves the object. Third, in the ball sorting task, we simulate dim lighting conditions where the golf ball and the table tennis ball appear visually similar in shape and size. The robot must identify and pick the golf ball. The vision-only policy frequently misclassifies and grasps the wrong object, while the Visuotactile policy correctly distinguishes the two and completes the sorting. We now show policy rollouts of real-world gear assembly to demonstrate how tactile feedback enhances policy performance. In this task, successful insertion requires precise alignment between the teeth of the 2 gears. The vision-only policy fails due to misalignment, a subtle contact error that vision alone cannot reliably detect. In contrast, the tactile force field augmented policy perceives contact deviations through force cues, enabling fine alignment adjustments and resulting in a successful gear assembly. We now present policy rollouts of real-world bulb installation, showing 3 representative cases. In the first case, the vision-only policy fails due to under-tightening. In the second case, excessive rotation leads to over-tightening. In contrast, the vision plus tactile force field policy achieves a precise, snug-fit installation. We next show representative rollouts of the ball sorting task in the real world under both normal and dim lighting conditions. The robot must sort the golf and table tennis balls into the orange and blue bowls, respectively. Here, the Visuotactile policy, augmented with high-fidelity tactile images, successfully completes the task. We also present typical failure cases from the vision-only and vision plus tactile force field policies in real-world ball sorting. Thank you. We will release our codebase, datasets, training logs, and pre-trained checkpoints.